The only is the way not, I will like you. If you wanted to stay on. Swap these around. See, or this. Side, it'll stay on. No, that's. That side. And reverse the direction. So it's a 50-year down. He has no idea. No, I've never had anyone talking about this. I mean, he's completely. Well, I still know how it works, so.
Street's fault is goes on top of the can, back, so it dumps in and then it goes up and then it like. Yes, good. I think I have, like, in case it falls off the track, I think have like a phone thing that leads onto separate paths. That's another reason we can use the plastic switch pad or phone big wall, that it won't other way. The legs, like, the more important part.
Okay, hand back some things.
Yeah.
You know, like, our new spots.
Cheers, can you rubber bands to the ball, like the.
But- Mother, I had three around. Yeah, that's right.
Like, I want it, three, yeah.
You're today. There you go.
Oh, cool.
Yeah.
Well, it's already over.
Yeah, we can use that as a part.
Whether we have it, focus on. So, and some of you, so you have a second question. I mean, not all, but but the thing on the forum, you can't do away with anything. How do you then use the Yes.
There we go.
You got
We'll be in 6 minutes.
Hold on, Lewis. Hold on, I'm coming. I'm putting my voice on. Already. Oh, you're there.
That's sort of smoking.
Okay, I got that down. I will post this, what we have for forum, and give an idea, if you want to bring. And then. Yes.
Oh, that's adoption thing, it's called factory default, we reset it like that. Put it up, I'm serious. His ear cold back.
Do I?
That's right.
No, anybody.
That's right.
Auntie. Oh, yeah.
Auntie doesn't like me.
Well.
Sorry, you get it?
Yeah.
Auntie.
I mean,
You make sure that she's got,
did I hand him one?
I do not know.
This is over to see every single one.
Every single lab in the world. Yeah, I make that accessible. I think we need to say that. You did good?
I do know. I literally just think about everything.
Yes, you did great. You got time. According to the 3 students in question, they're not coming back, so I need to double check with parents if that's the case. You're the person one remaining slot. So I will let you know hopefully this week. I mean, hopefully within a few days. I just want parents to say it, not that they think.
Yeah,
Yeah.
that's amazing.
Yeah, I know, it was, overnight, which freaked me out. We've never had that quick.
And I know, I don't wanna hold you up, I also saw in the homeschool community that you host a dance.
Yeah.
I'm
yeah,
like,
they
oh,
do.
that's
Fun.
kind of weird.
Well, the dance thing was just because there was like, you know, every dance I saw was like a costume theme or something. And I'm like, can we just do a real dance?
Right.
So our clubhouse is great for it. It's a good size. It's not too big. It's not too intimate.
Mhm.
And we usually have 60 kids. And I mean, we have everything from like the dog crew to like the one last year where my mom's prom dress. Like we have everything. And they had so much fun. And
Yeah.
we just play whatever, they send requests all night, my husband sits there and just DJs for the whole night and has a blast, and
Oh, that.
then, yeah, and you know, we cover the rental fee, we cover the food, cause we have food and drinks.
Yeah.
Bailey's been 3 years, dance,
Oh, I've been 2 years, but
2
yeah.
years, yes,
Okay.
fun, and.
It's
sorry.
fun.
Okay.
And then anything that's extra, I just throw it back in the program, because I'm not doing it for profit, so I throw it back in the program, so I've got my eyes on the countertop dishwasher for Kim. Cause there's a lot of glassware, so yeah, it's like a bonus, you know, if I get enough to actually buy something with it. So, yeah. Great.
All right.
Well, hopefully you'll hear from me in a couple days. Well, you'll hear from me in a couple days, no matter. Hopefully it'll be good to go.
Okay, that would be
All set.
fantastic. Thank you so
Yes, no,
much.
thanks for joining
Good.
us today. I really appreciate you
Yeah.
coming out and
Did
giving
you
it a
see-
shot. He's done great. He answered questions. He's got coins,
I
so he's
see
cranking
that,
out
yeah.
coins. So I mean, that.
You had him at candy.
Yeah, it works. Let me tell you, it really works. I wish I'd figured it out.
Brilliant.
Neither one. It took a
Yeah.
little while, but
I might implement that for the rest of this year, this school year.
I'm telling you, it works, man. You have a great day. Thanks for coming by.
Thank you so much.
Yeah. You
Oh,
you
yeah.
are. Okay, everybody start picking up and heading in.
Compass fell off.
I'm
The
sure.
compass.
Okay. That's okay.
No, don't do it again.
Oh, I see. Let's see.
Magnetism.
Jordan, Chloe, you know where Chloe is, and I know where Drew is. Looking for people. People. I'm seeing Chloe. So big. I had a friend from church who studied at here. You see that? Did I? Every day, it's every color yarn, and whatever the temperature makes it, so it's like this beautiful, and it tends to be kind of a spectrum, you know, because the reservoir. I like it. I can straighten it like a scarf, but beyond that, nope. Nope, don't count on me. All right. Standard. Look at it. Bailey sits right there. Each other sits right here. There. Beautiful. You go. All right, then we're ready to start. Round it up, folks. Let's do it. Okay, this is my love. So I'm gonna find this one with mine. And yeah. Here. By the way, just put your Q4 on the table over there.
Yeah.
All right, if y'all will throw all the snap get stuck in the bin. You can attach me there.
I'm sitting there. Yep, my backpack right there.
He was sitting in my spot.
That's what I'm trying to. No, no, not where I'm sitting. I'll go away.
I will.
I just moved through.
Thanks for having another round of time somewhere.
Not a dog.
You sit, let Lucas sit right there.
Yeah.
See,
No, let Liam sit there.
Yeah.
No.
If he sat, you can't make a move.
That was my spot.
It's well, then you're sitting on. It's fine.
Yeah, so I gotta. Okay, good. I think we're good. All right, real quick, still have Mrs. Bailey. Oh, you're all backlit. All right, Asher, Milo. Okay, Asher. Lots of stuff to hand out and hand back today. Here you go. Okay, Drew. One last set of stuff to hand out or hand back. Raise your hand if you are captain for Q4. All right, this is gonna be the only thing you hand in up until the day he presents.
Oh.
And who's next?
Oh,
Who is else as the captain?
Weekly log, okay. I
Yeah,
figure out what this
should just be
was.
3. Did I think more than 3?
Uh,
So I had you 6. Here, hold on.
You could.
And in the extras, those are my extras.
Like,
They're on the bottom, not
they
the top.
all have the same date, so.
James, you're up captain.
These are only 3.
Did I give you the same date ones?
No,
Okay.
it's only 3 days.
That's right, 3
Okay.
weeks. It should be 3 weeks worth.
Great.
James.
Which is all captain.
Anybody else already? PJ? Anybody else in charge? Drew? Okay.
I have them.
All right, so those are, put those in the back of your binder. You're just gonna, at the end of lab, you're gonna hand in whatever the date is for me. And it just basically says, these were what we did. So I know that you're actually doing something besides just like gallivanting around in the woods, looking real excited. Cool.
I have
Cool.
a question. Are you
Yeah.
gonna assign us areas or do we get a take this specific?
So good question. So here's how it's gonna work. We're gonna cordon off 4 areas right outside the gate into the woods. And I'm gonna, yeah,
Okay.
beyond the gate. And I'm going to box them off with tape, you know, like I did with biology when we cordoned off areas for observation. And so it'll be staked and cordoned off. And then we're literally gonna have your captains draw straws for which of those areas you get. So they're gonna have, you'll get your area based on what straw you get, which means some of you may have more slope than others. Some of you may have trees, some of you may have no trees. I'm gonna do my best to make them as egalitarian as possible, but yeah, Drew. Oh, I'm sorry, I thought you were talking to me, you know, because I'm in charge, but that's okay. All right, so, yes. Do what? Yeah, yes, I saw that one's, no, I caught that one. All right, so real quick, y'all saw the numbers for next year. Thank you for referring friends. That's amazing, like super amazing. I'm still in shock. And also the dance. I put that in the last email. Some of you, yep, some of you already signed up for it.
I don't know if I've already signed up, I just know I'm gonna sign up.
I think you already have. So wait, who's been to the dance before? So about more than half of you. So if you haven't been, ask them. They did have a good time or they wouldn't be coming back. We've already sold 26 tickets. We only can do like 75. So that's already great. I mean, we just had a gangbusters week, apparently. It was wild. So yeah, so keep that in mind and get your tickets. Anything that is over what we pay for the venue and what we pay for the food and drink, anything that's left over money-wise rolls back to the program because it's just I mean, I don't want it, so it's not for me. So I've got my eye on a couple things, including, like I was telling Bailey, a countertop dishwasher, because that glassware for Kim sometimes takes me 2 hours to clean up. So it'd be real nice.
So much.
Yeah, it's a lot. So it'd be real nice to be able to pop it in a dishwasher and let it get done. That'd be super. All right. So electricity and magnetism at work. Oh, also real quick, your Q4 package, you'll notice they're a little thinner than usual. That's because our lessons get a little more, look, we're just kind of touching on those chemistry topics because Q4 is all chemistry. It just kind of gives you a kickstart into next year. So we just kind of touch on stuff. It'll be pretty fast. And if we wrap up early with juniors, you know, then I can say, go ahead and get out there and start your lab. If it's one of those lab weeks where you're outside working on your Rube Goldberg. All right, cool. Excellent. Any questions about any of that? Everybody has a Q4 packet, right? All right, then you're good to go. I will, in this week's weekly email, I will include your unit test study topics list a week early. This particular quarter was one whole unit, just the way the curriculum works out. It's all one unit. So that means the test is basically a whole quarter. So it's a lot of stuff. It's a longer than usual test, but I don't think it's harder than usual. It's a lot of material. It's not particularly difficult concepts, but still it's a lot of material. So give you time to study it. All right, electricity and magnetism. Let's check it out. Magnets, magnetic fields. Hands are already up. I haven't gotten to the question. Somebody define magnetic force for me. All right, Yusuf.
The force of magnet or a similar metal.
Okay, so the force a magnet exerts on another magnet, iron, or a similar metal. Not all metals are magnetic, right? Only some? Okay, and what are magnetic poles? All right, Lucas.
The regions where the magnetic force is strongest.
Okay, yeah. So these are your regions where your magnetic force is strongest. One is positive, one is negative. That's how we term it, right? A positive and a negative pole. All right. Now, what's a magnetic field? All right, PJ.
A field that surrounds a magnet and can exert a magnetic force.
All right. So yes, we have this field surrounds a magnet and can exert a magnetic field or magnetic force. Yes, I should say force really, but yeah. All right. Now, a magnetic field, which is strongest near what end of the magnet or what part of the magnet? Xander. Strongest near the poles will either do what? Milo. Repel or attract another magnet that enters the field. Now, y'all have done this before, right? Everybody has done the thing where you got two magnets and you're trying to push them together and they're repelling, right? We've all played that game. It's fun. And I think week before last, we had out the round disc-shaped niobium magnets, and we were kicking them off on the counter, spinning them like coins, and you can watch them. They get far, depending on how they're oriented, they'll either push away or they'll slap together. That's fun. We may be able to do that next week if there's time. Next week's a lab that requires patience. It's not hard, but it takes a lot of fiddling sometimes to make it work. You're going to be making electric motors next week, so it's good fun. All right, so what's the magnetosphere? Caitlin.
The area surrounding that is influenced by
Right. The area surrounding Earth that's influenced by its magnetic field. And you can think of it almost like a big old donut.
Question. Provide a glue gun that we could use for the people.
I do have glue guns. Those are part of our regular lab supply inventory. So yeah, what I may do to make it easier for you guys, I gotta figure a way to make this so that you can read it. But I can find a way to publish a list of all of the lab supplies we have, like all of them, which is a lot, so that you can kind of see what exists. There's going to be some things that obviously I'm going to be like, no, you're not taking that outside and using it. But
Okay.
a lot of stuff will be accessible.
Okay.
I was trying to put together like a checkout library on the website, but that's taking like way too much effort and energy. I'd rather put that towards your lessons and stuff. All right. So those of you who've been watching the generator and fussing with the generator, Colin's been fussing with the generator, Drew's been fussing with the generator. Okay, I know this dude is like an eighth of your age, but he does the best and cleanest and clearest explanation I've seen. So instead of the little light, like we have the little LED, he has a little flashlight, but he gives a great explanation here for how it works.
They're feeding. The light is the light.
I like JoJo now. He's one of my favorites.
Hello, welcome to JoJo's Science Show. Today we're going to explore dynamos. And I'm going to show you how easy it is to find a dynamo. You know what a dynamo is? A dynamo is a machine that can turn movement into electricity. So how does a dynamo do this? Here I have an electric motor from a printer. Many toys have electric motors. Electric motors have magnets and copper coils. When the magnets move near the copper coil, it causes the electrons in the copper to move and makes electricity. This is called magnetic induction.
Oh, dude.
Hello.
Let me pause him for a minute. Let him buffer while he giggles. That maniacal laugh there that I'm a little concerned. Right? But dude, he's spot on. He knows what he's doing.
Magnetic induction was discovered by British scientist Michael Faraday. And he was able to build a dynamo or a generator. A lot of the electricity we use today is made by magnetic induction. The giant turbines all have magnetic copper coils and use magnetic induction. For this experiment, you'll need an electric motor, 2 alligator clips, and an LED. First, connect your alligator clip to your electric motor right here on one of these things. And you connect the other side to one of the sides of the LED. And you do that same thing with the other one. Okay, see? It's as easy as that.
The maniacal laugh worries me, man. But
See how when you turn it, it blinks? But you have to turn it one way because this is an LED. The LED is a diode that only allows the electricity to flow in one direction.
okay, keep that in mind when you're talking about this thing. LEDs are diodes. Diodes only allow electricity to flow in one direction, but somehow they're both lighting up, right? Even though we have an alternating current situation going on. Okay.
This electric motor is turning the motion of my hand into electricity, and it's lighting up the LED. Oh, look, it's Eli the electron. He's going to help explain how dynamo.
The electron.
You see the dynamo on top? You see the magnet on the outside and the rotating copper coil on the inside? When the copper coil moves past the magnet, Eli starts feeling a force that pushes him around the circuit. And this causes Eli to light up the LEDs. This force is called voltage, or electromotive force. If this electric motor had a handle, we could see the LED lighting up. So that's why we bought a dynamo kit. If you buy a dynamo kit like this one, you can build a dynamo with a handle. That makes it easy to spin, and here's the dynamo motor really fast. First, I'm going to thread these 2 wires through this
I
hole.
think you can
right
buy that at
here.
Hobby Lobby. Definitely Amazon.
This LED. Next, I'm going to install the 2 gears. So you can see the inside of the mini machine. And now we put this. Now we're going to screw together our case. Next, we're going to attach our LED wires to the motor. And this there.
Mhm.
Look, this handle makes it much easier to light up our LED. Now we're going to finish putting together our torch. Wow, it works! The gears work because when I spin the handle 1 revolution, it spins the motor many more revolutions. You can't see me, but now you can see the fly.
Very excited to show you
Some
this.
science with JoJo Science Show. If you like this video, hit thumbs up.
I like your video, Jojo. You're a cool kid. Woo! Made that maniacal laugh again. Way to go, Jojo.
I like Eli the electron.
Hey, Eli the Electron is pretty cool. I like him because he's got it together. Little hope for the future, right? When I look at that, as goofy as that is, I'm grateful because I don't know if y'all remember, but well, let me see. I think I actually talked about it in chemistry class, so Bailey might be the only one that remembers. But do you remember there was a survey, a European survey that asked questions, true or false questions, and one of them was, "I would love to live in a chemical-free world," and the majority of them said, "Yes, I agree."
No light bulbs,
No anything,
yeah,
nothing.
no air.
Life is chemicals. Where everything in this room is chemicals. I'm like, boy,
I
that's
think there were more things, oh, no food. it has chemicals.
yeah, that's
But
definitely
even
what they were
then, like,
thinking. But it's a great example of scientific illiteracy, right?
yeah.
All right, so we've seen how the little dynamo works. That one at least. And I know some of you got a really good look at that. All right, that's how a dynamo, like a small one like this, or like the little JoJo, God, get that terrible name. His, just call him Joe or Joseph or Joey. I don't know. I'm always, now that's forever going to be a JoJo Siwa thing for me. By the way, did y'all see JoJo Siwa was pregnant apparently?
What?
Yeah, I saw that yesterday. I'm hoping it's not true because that's just scary. I don't know how old she is now, but yeah, she's in her 20s, but I still was like, whoa, dude. That rocked my world. Messed up my entire perspective. All right. So apparently. So Earth is actually a dynamo itself. So here is how Earth functions as a dynamo.
Mars. So do you guys know that Mars doesn't really have a magnetic north or south? Because of that, Mars doesn't have much of an atmosphere. Mars has a very thin atmosphere. But we're finding more and more that Mars actually used to have an ocean. Still has a little bit of ice on the poles where it's cold, but it actually has
back there?
a lot more. We know that because it has a lot of sedimentary rocks, sedimentary features. So I got a demo today
Come on.
that actually shows you guys how the Earth's magnetosphere works. So this is kind of one of my favorite demos. The first thing let's talk about is how you can form a dynamo. So this is a schematic cross section of this dynamo that I actually have here today. So when I spin the rotor, I want you guys to also see that rotor there. So really all a dynamo is metals moving past each other, right? But it actually generates a magnetic field. So check this out. So this is a magnet that's out of a hard drive of a computer. So it's neodymium metal, but it's extremely magnetic. Is this plexiglass at all magnetic? Can it actually do anything with electricity? Can it conduct electricity? So what do you think is going to happen when I drop this magnet down the plexiglass? It's going to go pretty fast, isn't it? It's going to go basically the speed of gravity. Ready? I get a countdown. Why are you plugging your ears? We don't have any explosions today, I promise.
Why are you plugging your ears?
Right. You guys ready?
Yeah, today.
Countdown. 3, 2, 1. Was that sweet or what? Now, I achieve aluminum. Is aluminum magnetic? It's not, is it? Can it conduct electricity though? Yes, in fact, you go to a Home Depot or a hardware store, you have the choice of buying aluminum wire or copper wire. Check this out. Now, if I blow your mind, I want to hear some oohs and ahs. You ready for this? So you've seen that it does not skip the aluminum, right?
They're fun.
Watch this though. When I let this magnet fall, watch how fast it falls. Oh, come on, you guys can do better than that. I want more oohs and ahs. You guys ready for this? Here we go. So this shows us that something that's electrically conductive, like this aluminum, can actually generate a magnetic field. You guys want to actually check this out on your own? All right, so I'm going to pass. I got 3 of these. That's what's called the lens effect. I'm not going to test you on it, but you first have to understand that before we can actually talk about how you make a magnetic north and south pole just with motion. So believe it or not, the Earth, when we look into the section of the Earth has a core, doesn't it? So right here, everybody see that? So we basically, this is a cross section of the Earth. You can actually see that it has a core. The core is made out of iron and nickel, isn't it? Is it solid? Is our Earth core solid? It's not solid. In fact, the outer layer of the Earth's core is liquid. So that liquid is actually kind of moving its own speed in the core of the Earth. And it's that motion of a liquid metal with a solid center core, and all that interacts to actually make a north and south pole. So you want to see what happens when we do this with a dynamo. So because we don't have the size of the Earth, this isn't very efficient. So what I've had to do is kind of cheat it a little bit to put a coil of wire here. This is a broken compass. So if you guys ever go farther in geology, you might actually own one of these.
Broken
Check
compass.
this out. So everybody can see that. So right now that brunt is pointing to the north, right, up to the Catalina Mountains. So I'm gonna spin the rotor of this dynamo. You guys ready? Look at that. So you can see me down there spinning this dynamo. So this dynamo is actually what's happening in the core of the Earth. Because we have a liquid outer core and a solid inner core, it's basically doing this spinning, and that generates the magnetism. And now you might be wondering, big deal, why do we care? Check this out. And so we have formed this magnetosphere. And if you want to learn a lot more about this and see amazing computer graphics, check out this YouTube link. It'll take you much further than we have time for in class. But that magnetosphere actually protects us from the solar wind. Without a magnetosphere, without a magnetic north and south, that solar wind would actually strip the Earth of all of our waters and gases in the atmosphere. So we would look a lot like Mars. You might be thinking, that's not bad, right? Would you guys like to live on a planet like Mars here? Or would you rather live on a water planet like the Earth? I'd like to live on the Earth. And so that's all because we have that liquid core in our planet. And so the cool thing is that we have this magnetosphere basically around the, protecting the Earth, planet Earth this way, but we also have these poles. It's like a big donut, isn't it? So the poles are where a lot of this solar energy can actually enter the Earth. And so that's why we get these auroras. And so we get the aurora borealis in the north, we get the aurora australis in the south. And so these are charged particles from that sun energy that basically form plasma, and they rain down in the poles because that magnetosphere is weak at the north and south pole, but it still protects us. So that is the reason why we're still here today. Just because we can generate a magnetic north and south pole, which protects us and holds all of our volatiles in, the waters, our gases, and everything. Any questions on that?
So that's interesting. Yeah.
So what's,
So,
I guess there weren't any.
Hang on, wait a minute.
so that's how the magnetic poles is generated,
Mm-hmm.
and Mars doesn't have poles,
Mm-hmm.
but it did have water, which means that it once had poles. How did it lose its magnetism?
Or it means that it never had the poles and the solar winds stripped away all the water that it
How did it
had.
have water in the first place?
Well, the poles don't create the water, but the poles create the magnetosphere that
Yeah.
keeps the water in.
So if there wasn't anything keeping the water in, then how's the water in the first place?
Well, the water can form, but then it can also go away. It can evaporate out into the atmosphere because there's nothing to keep it in, because the solar winds are just going to sweep it right off, which I think is what they are suspecting happened with Mars. So interesting. Yeah. Oh, you ready for the next one? So that, yeah. Are you ready for the next one too? All right. Okay. So magnetic domain. Caitlin, you go for this one.
A region that has a very large number of atoms with aligned magnetic.
There you go. So a region that has a very large number of atoms with aligned magnetic field. And then Yusuf, what was this next one?
A material that can be magnetized.
Right, ferromagnetic material. So can be magnetized because it contains magnetic domains. There's a root in that word. Do we see it? What's the root in that word? Ferromagnetic. What is that, Jordan? What's
I
ferro?
have no idea.
You're right that it's ferro. James. Iron, right? We think of iron as being kind of like the primary example of magnetic metals, right? So
Iron's thing on the periodic table is Fe.
yes, iron is Fe on the periodic table. It's ferrous. And that little bottle of stuff is ferrofluid. Yep, the one that I think Emma had it last. I think it's up there on the counter. But yeah, this ferrofluid. Everybody see the ferrofluid? Has everybody had a chance to play with the ferrofluid? That you can take it, James. Yeah. It's really impressive. Like, it's just way fun. I could look at it for way too long. Suck my life away. When a material is magnetized, most of the magnetic domains are aligned. All right. So, permanent and induced magnets, not the same thing. So let's have a quick look at this one. This is a short video.
And today,
Hello.
this video, we're going to take a look at what we mean by a magnetic material and the differences between permanent magnets and induced magnets.
Hello.
Now, one of the confusing things about magnetism is that not all magnetic materials are actually magnets. An actual magnet is any object that produces a magnetic field,
Man.
while a magnetic material is any object that can be influenced by a magnetic field and has the potential to become a magnet. When we talk about which elements are magnetic, we're often referring to which ones are magnetic materials, not necessarily magnets. For example, even though nickel is a magnetic material, only some pieces of nickel will actually be magnets. The other common magnetic elements to know are cobalt and iron. And the alloys of these elements, like steel, also count as magnetic materials. And to help you remember this group, just remember that the first letters of each of the words spells NCIS.
Oh.
TV shows.
When
That
we
always
think
works.
about magnets, like a common bar magnet, what we're really thinking about are permanent magnets, which produce their own magnetic field all the time. There are another group of magnets, though, which we call induced or temporary magnets, which only have a magnetic field temporarily. These are made when a piece of magnetic material, which wasn't actually a magnet, like your average piece of nickel, is put into the field of a permanent magnet. This induces the piece of magnetic material to develop its own magnetic field with its own north and south pole, and thus we call it an induced magnet. And a key point to remember with induced magnets is that the force between a permanent and induced magnet will always be attractive, which is why the left side of our piece of nickel became a north pole rather than a south pole. If we then remove the induced magnet from the magnetic field, though, then it will lose its magnetism. Some magnetic materials, like nickel and iron, lose their magnetism really quickly, and we call these magnetically soft materials. Others, though, like steel, lose it more slowly, and we call these ones magnetically hard materials. Anyway, that's all for this video. So if you enjoyed it, then
Love the
please
giant
give-
pause before he says, "No, we're really done."
And we'll see you next time.
All right, so we have induced and permanent magnets. All right, so nowadays, most widely used permanent magnets can be classified into 4 types. Anybody want to guess? So we have neodymium, iron, boron. Okay, these are rare earth magnets. What's it mean to be a rare earth magnet? Do you know, PJ?
Rare materials that come from the earth.
Yeah, rare earth metals are on within a particular organization on the periodic table, and they are those that are a little more difficult to find. GM developed these, as in General Motors, right? Back in 1984. They're commercially available. They're used in things like MRIs, motors, switches, loudspeakers, everywhere, okay? And the neodymium ones tend to be nice and strong. Now we also have samarium cobalt. These are also rare earth. They're developed in the 1960s. They're resistant to demagnetization. They're expensive. They have good temperature stability, and they are hard and brittle. Then we have ferrite. Okay, there's what do you suppose these subscripts mean? You want to guess, Bailey?
The amount of iron and oxygen in it, so if there's X iron, there's Y oxygen.
Yes, yeah, it just tells you how much of each of those atoms is within this particular molecule. All right, and then these are ceramic-like, hard, brittle, generally gray or black, polycrystalline, made up of a large number of small crystals composed of iron oxide and 1 or more other metals in chemical combination. This is what you used in lab today. That's this guy right here is 2. There's 2 of them in there. They sometimes they'll call them ceramic magnets because they're that's the material they put them in. Ooh, I don't want to get pinched by that thing. I know it'll get me. And then the last one, they call these alnico. And this is great. Aluminum, nickel, cobalt. They've taken the chemical symbols for aluminum, nickel, and cobalt and put them together in a way that actually makes a word. So alnico. So these are a series of alloys. They make powerful permanent magnets. So primary constituents are aluminum, nickel, and cobalt. Sometimes they have small amounts of copper, iron, and titanium. They're very hard, which makes them difficult to machine. In this case, machine being a verb, as in difficult to cut them, mill them, whatever it is you need to do. And they are usually cast into their final shape because they're difficult to machine. And then subjected to strict regime of heat and magnetic field treatment. All right, so these are used a lot in industry. All right, here are some magnets.
Magnets attract certain metals and each other.
We got a lot of
That's
British
handy
people
for
today.
molds sticking stuff to the fridge. They help run motors and generators, among other things. Magnets occur in nature, but 2 centuries ago, people figured out how to make them using electricity. You could say it was a take-charge situation. You can't see or feel the force causing this globe to levitate, but it's not magic, it's magnetic. To make magnets, they must first create a
Real
sample
similar,
of the
yeah.
magnet shapes. They load this pattern of 4 magnet shapes into a machine that fills it with sand. Remove the pattern.
It is. Watch how it's made all day.
While the machine's lit.
Oh my
Then it's
God.
back inside, but this time the machine puts in gases to chemically harden the sand. It takes just seconds to solidify. They lift out the sand slab, revealing the impression of the magnet pattern. It's now a mold. Magnets come in many shapes and sizes, as do their molds. Now they're ready to mold the magnet shapes. They take copper, cobalt, sulfur, nickel, pure iron, aluminium, and titanium.
Yep,
They roll all these
aluminium.
metals into an electrical induction furnace. It generates a pulsating electromagnetic field that heats to more than 1,600 degrees Celsius.
That's
Turning
hot.
everything into a molten soup.
That's real hot.
They pour this into the sand molds. The molds burst into flames because the gases that harden the sand are highly flammable. They slide the blazing molds to another part of the foundry and knock them to the floor. Then they bust them open with a sledgehammer to get air inside so they cool down and the gases burn off.
This is a hot job, man.
They shovel everything into a bin and sort the metal shapes from the sand chunks using what else? A magnet. The molded pieces react like ordinary metal. They don't yet have magnetic power. Some are shaped like rings. Threaded onto a copper pipe, they'll be used in electric motors. They place the ring-covered pipe in a much larger tube. Then they center it by packing silica sand tightly around it. The sand will hold the rings in position during the next step. They seal both ends with concrete, allowing the inner copper tube to protrude slightly. Then it's into a different electrical furnace. It heats the tube full of magnet shapes until it's red hot. This primes them to accept an electromagnetic field which will be delivered by this metal rod. They slide it down the center of the copper pipe and clamp it in place. Water keeps the pipe from melting as they deliver a low voltage, high current charge in a cylindrical formation, important for motor magnets. They break open the seal. The process has left the ring shapes mildly magnetized, but most importantly, it's orientated the magnetic field properly. They grind away any rough edges. At this point, these magnets are pretty useless, but this machine will empower them. It delivers an electromagnetic charge to the metal, which magnetizes it. The establishment of that weak
Got a
magnetic
sweet
field earlier
mustache.
has laid the groundwork for this moment, ensuring that the magnetization is properly orientated. Now that's some serious magnetic muscle. In their various forms, magnets continue to exert a lot of pull in our society because their invisible power helps keep so many things running.
I seriously wish How It's Made was still like running because that show is amazing. Okay, 2 questions. First question I have is, why do you think they use silica? And the second question I have is, why do you think it primes those metal pieces to have them superheated before they start running the charge? Okay, Bailey, you have a guess on one of them?
Have like a really, really high melting point.
Yes.
Like it takes so much to work to melt the sand or silica compared
Yes.
to the metal.
Yes.
So that way,
So-
that way the sand or silica doesn't melt.
Yes, so silica is the mineral with like the highest melting point. So when molten rock is forming, it's the silica that will crystallize first. That's why in granite you have the little quartz chunks within it. Quartz is silica, pure quartz is silica, largely, almost entirely. So silica, it has to be super, 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 super hot to melt, like way hotter than any of these metals. So that's why they're using silica, because they can basically pack it around those little pieces of metal. They're not going to shift and the silica is not going to melt. So most sand is full of all kinds of stuff. Like if you go to the beach and you ever put that sand under a microscope, you find all kinds of things in it, little pieces of shell and whatever. But sand that comes from ground up quartz is pretty much pure silica. So you're not going to be able to get it hot enough to melt it, really. Not doing this. Why do you think they need to be hot in order to best accept the charge? James. Yeah, when the metal is softer and it's everything in there is expanded, the space between the atoms are expanded, they're more likely to be able to turn and orient the way they want them to, so that you get the poles you want. All right, so electromagnetism. Now we look at electromagnetism. All right, so what is electromagnetic force? Ridley. Yep, so it's one of the 4 basic fundamental forces. And in the universe, we have what we call our basic fundamental forces. And it affects all things in the universe because it has a limitless range. It has both attractive and repulsive properties due to the 2 charges that it possesses, namely negative and positive, right? So like charges repel, unlike charges attract. So you can see he's working on an MRI machine, or he's about to go. I don't know what he's doing. He's straddling the MRI table. I don't know what's up with that. But this is where they're using a lot of these magnets and putting the electromagnetic force to work in a way that we can actually get data from it that's helpful, right? Very cool. We talked about before. Who's had MRIs? You had an MRI? Nice and loud, right? Hear all the magnets switching? Yep. All right, so the 4 fundamental forces, we talked about this a while back, but just as a reminder, they're gravitation, electromagnetism, it has an extra C, I think, but I did not make this, strong force and weak force, right? This is weird. I don't know why somebody's added that, but I didn't write that. This is just a graphic. Weirdness. So yes, these are our 4, and electromagnetism is great because it's traveling far. Yeah. Usually strong nuclear forces. Yeah. All right. So this is interesting. All right. Now Maxwell, this dude Maxwell, if you go into engineering, electrical engineering, probably also maybe chemical, a lot of electric. There's a bunch. Maxwell is this guy who basically defined all of the equations that are used for any sort of electromagnetic, anything in physics beyond basic physical science. Start getting into Maxwell's equations, and he's kind of a big deal. Shh. All right, so moving electric charges create a magnetic field. We know that. Forces acting on moving charges. So electric fields cause charges to move in what, Liam?
Same or the opposite direction.
Same or opposite directions. And magnetic fields cause charges to move in what? PJ? Or no?
And not perpendicular?
Okay, yeah, in a perpendicular direction. All right, so what's that mean? All right, so have a look here at the graphic. You see a little graphic here with the Maxwell's right thumb rule and then Fleming's left hand rule. Okay, this is what it means. If you take your right hand and you imagine that you have a little pole in it, like in that first image there, if the current is going in the direction your thumb is pointing, then the magnetic field is going this way.
The way your hands are curled.
Yes, I was about to say the way your fingers curled around the imaginary rod. So current goes like your thumb, magnetic field curves in the same direction. Now, if you were doing Fleming's left-hand rule, this one shows you that you've got your electromotive force is going this direction, your lines of flux go that direction, and then your current goes this direction. Probably the most helpful one for anything that you do beyond this class, that is anything with the electromagnetic field, is that right thumb rule. Sometimes they'll call it right hand rule, but if you remember that, you know, thumb up, fingers curl, that's how your fields are going to work. And if there's time at the end of this class, I'm going to show you this video I just got last night. Jason actually sent it to me. He's like, this is great, but it explains how power travels through our power lines basically. And it's not really how we think it is. It's much more complex. So solenoids. All right. What's a solenoid? Caitlin.
A coil of current carrying wire that produces a magnetic field.
Yes. Where would you find a solenoid? Anybody know where to find one? Do you know? No, no. Maybe. Do you know, James, do you know? Do what? Phones, maybe? Okay, Drew, what?
One in the Mustang.
There's one in the Mustang. There is. Where's the one in the Mustang?
My Lego Mustang.
There's one on your Lego Mustang. Okay, that's important. So the one on the Mustang, where is it?
It's like on the opposite side of the power steering unit.
It's opposite side of the power. Yeah. So it's mounted to the frame. It's an electromagnet. Yeah. And if you have an older car, especially if your battery's dead, but you have just enough charge for your little starter motor to kick, you'll hear this sound that goes tick, 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 tick when you're trying to turn it on. That's the electromagnet within the solenoid moving. That's the physical movement of that. It's moving the magnet to complete a circuit, but then you don't have enough power from your battery to actually kick everything on, but you can hear it click, 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 click. I think I have a video in here I do, I think, on how to bypass a solenoid. So if your starter motor is dead and that's your problem, there's a way to start your car without it.
That's the issue.
Your granddaddy is famous for doing it. I've done it once at his instructions, scared me to death, but okay, electromagnet, Jordan.
A solenoid with a ferromagnetic core.
Yep, solenoid with a ferromagnetic core. Okay, so changing the current in an electromagnet controls the strength and direction of its magnetic field. All right, this video is a bit longer, all right, but it'll help you understand where solenoids fit in. It's not really that long. It's only 3 minutes. It just feels long, and I don't know why it feels long, but it's got really good graphics that make this whole thing clear.
It causes a small current.
Hello. That's weird.
When the ignition key is turned, it causes a small current of electricity to flow into the solenoid coil. The solenoid is usually made of two coils, known as the pull-in coil and the hold-in coil. The end of the holding coil connects to the casing of the starter motor. So the current returns to the battery by the frame of the car. The pull-in coil is connected to the main output terminal. Both coils are energized to create a strong magnetic field. This pulls the piston back, and as the contactor plate connects across the main terminals, both ends of the pull-in coil will become the same voltage. There will be no voltage difference across this coil at that point in time, so the coil will turn off because there's no current flowing through it. It takes far less energy to hold the piston in position, so the hold-in coil continues to run. As the piston moves back, it's going to pull on the lever. This pivots and transfers the motion to the drive sleeve, pushing it forwards. As it moves forwards, it slightly rotates the pinion, allowing it to lock the rollers in the clutch and slide the pinion into the flywheel. As the contactor plate connects across the terminals and turns the pull-in coil off, a very large current will now flow through the contactor plate, through the thick wire, and into the brushes. From here, it flows to the commutator plates and through the coil. Then back to another commutator plate and through another brush, which is grounded to the frame of the car. So the current returns to the battery. The coil produces an electromagnetic field, which interacts with the permanent magnet or field winding in the stator. This interaction causes the rotor or armature to rotate very fast and with a high torque. The rotor transfers it through the shaft, through the clutch, and into the pinion gear, which turns the flywheel. As the flywheel starts the combustion process, the engine will eventually begin to rotate the flywheel faster than the starter motor. This unlocks the overrunning clutch, so the pinion gear spins freely. When the key is released, it cuts the power to the solenoid coil, which releases the piston. The spring pushes the lever back, removing the pinion gear from the flywheel. The current is cut to the starter motor. The combustion engine continues to run by itself, and the alternator recharges the battery. We have also covered how the car battery works in detail previously. I'll leave a link for you in the video description down below. Check out these videos.
Yeah. All right, here it is. If you have a solenoid in your car and your starter motor is dead, been there with the Mustang. Okay, this is how you can start it.
Same as the battery?
No, it's separate from the battery, but it does use the battery. Yeah. So if your starter motor's dead, you're not even getting the click, 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 click. So here's how you do it. I've done this and this is crazy. You need a long screwdriver, okay?
Everybody,
It's fun.
do you have an old Ford? Do you ever run into a problem
Yeah,
when you turn the key? And no matter how many times you turn it, this is all you get?
Yep.
Well,
Mine
then
doesn't
stay
ding.
tuned, because I'm gonna teach you how to start your old Ford with a screwdriver. Now, this is meant to be only in emergency situations. You don't just do this, don't be doing this all the time for a week. But the first thing you do is just grab a regular, long, flat screwdriver.
Flat. Put your key in the on position.
Next thing you need to do is make sure your key is all the way forward. Okay. Then, the next step in all of this is you walk up to the corner.
That's the solenoid.
This, my friends, is called the starter solenoid. Okay, this is the power wire. And this little hideous one, this one runs down to the start. What you want to do is you want to make continuity between those two terminals.
Bypassing the starter.
By touching them both together. Now be careful, folks, it will start. That is not something that you should do all the time. But it will work, and if that does work, this is your problem. This is what's wrong. Everything else is working if that just worked. So your problem will be the starter solenoid. Now, nowadays on cars now that won't work because the solenoid is built into the starter, and then you have to replace it all. But if you have an old Ford like this one, you're in luck because you just jammed it up with a screwdriver. But don't worry if it is bad. One of these are only $10. Please just replace it and don't use my tip to go for a week without changing it. So there's a little quick tip. Thank you for watching.
So you're right, it is a Lincoln, but Lincolns are Fords. It's Ford, Lincoln, Mercury was the whole thing. So yep. Now it's one thing. See, you can't do this trick, but I have done this trick and it does that. It sparks like crazy. Now here's the thing. I'm assuming this man is driving a Lincoln with an automatic transmission because he neglected to say, if you have a manual transmission, you better be in neutral when you do this, because if you're not in neutral, what's going to happen? Yeah, you're going to get run over by your own car because you can be standing right in front of the hood. Yeah, so a lot of fun. Yeah, another way to do, if you have an old stick shift car, there's one other way to start it, especially if it's a battery issue and you don't, this stuff. There is a method called popping the clutch. It's kind of hard to explain, but
Oh, yeah.
basically, if you're alone, it's real fun. If you have friends, it's actually more fun. But if you have friends, they stand behind your car, you get in the car, and you put it in gear, but you put the clutch in, and they push your car. And when you're rolling real good, you just snatch your foot off, and it'll kick the engine on. However, if you're alone, you have to do this thing, which I have done, hanging out of the car, feet on the ground, running. You know, really great if there's a slope you can kind of aim it towards and roll down, because it will kick on. It's fun.
They doing Karate Kid?
Do they pop it? I think they do. Yeah. Yeah, there you go. There you go. There's an old school reference for you. Yep. But you may ask your parents if they've ever had to pop a clutch or bypass a starter solenoid. All right, so galvanometer. So electronic devices such as galvanometers and electric motors and loudspeakers change electrical energy into mechanical energy. What's a galvanometer, Jordan?
A device that uses a solenoid to measure small amounts of current.
There you go. A device that uses a solenoid to measure small amounts of current. So they often look like so. Little needle. Beep. All right. Electric motor. Somebody defined that one. Emily. Yes. All right. Now think about how you got here today. The answer may not be the same for everybody. Did the vehicle that got you here today have an engine or a motor? It's got one or the other that actually drives the vehicle. Does it have an engine or a motor?
If it's electric, it's a motor, and if it's a gas, it's a.
Yeah, if you have an internal combustion engine, like your car, you put gasoline in your car, you got here with engine power. Same thing, steam engine, that kind of thing, Stirling engine, guys at the back. If you have a Tesla or something like that, or one of those, what are those, Hyundai Ioniq or whatever those things are, then you got here with a motor. All right, so keep that in mind, because something like that might show up on your test, like explain the difference. Yes.
You have a hybrid.
Then you probably have a little of both going on. I think the hybrids, I'm not sure exactly how they function, but I think they have some degree of, anybody know how the hybrids work with regard to that? Yeah, exactly. But I don't know how that is organized exactly. I don't have one. All right. Loudspeakers. This dude's sneakers are my favorite thing. So how do loudspeakers work? I mean, check him out, man. He is. Anybody here just sit in front of speakers and listen to music and do nothing, just stare? Anybody do that? Just my husband? Okay, yeah. So I have to clean up every Tuesday and make sure everything's put away, because I drive gymnastics carpool, and that man loves to sit in the pub with all those giant speakers in there. And he pulls a chair up that's dead center, and he just sits there and listens. He just listens, like he just stares at the wall and listens. It's great because he's a real audiophile. Like he loves to hear the sound. So how do these speakers work? Okay, so inside a speaker is an electromagnet, and it's placed in front of a permanent magnet. The permanent magnet is fixed firmly into position, whereas the electromagnet is mobile. Okay. Now the pulses of electricity pass through the coil of the electromagnet. The direction of the magnetic field is rapidly changed. That's how you get this vibrating that you see in speakers, this kind of thing, right? And that means that in turn, it's attracted to and repelled from the permanent magnet, and it goes back and forth. Anybody ever seen a speaker function with the screen off the front? You can actually see the little diaphragm shake. Right, so that's what's actually causing those longitudinal waves that produce sound, because we know sound is a longitudinal wave. So the electromagnet is attached to a cone made of flexible materials such as paper or plastic. That'd be this dude right here, right? And it amplifies those vibrations. It pumps sound waves into your surrounding area towards your ears. And then your eardrum basically does the opposite. Your eardrum is vibrating as well, but then it's taking those vibrations and it's changing them back into electrical signals that your brain can then recognize. Inside your ears are itty bitty tiny hairs that are, but like in your ear, you can actually, there's some great YouTube videos that show how this works, but the electric charge is actually kind of like, that's where it's picked up and then converted through the nervous system cells that allow you to hear. It's pretty cool. So the frequency of the vibrations governs the pitch. We know that pitch is frequency related. The sounds produced, and then the amplitude is going to affect the volume. So you've probably seen a small quiet speaker and it's just barely moving. Whereas like the ones that are pumping, right? They're really moving. So in turn, if you turn your stereo up high enough, you might even be able to see the diaphragm covering the cone move. Everybody seen that? Anybody who's never seen that, never taken the screen off a speaker and seen it go? You ever seen it? It's pretty cool to watch. You can actually see the whole thing vibrate. It's pretty neat. So to reproduce all the different frequencies of sound in a piece of music faithfully, top quality speakers typically use different size cones dedicated to high, medium, and low frequencies. Do you know what we call the cones dedicated to high frequencies in speakers? Do you know? Tweeters. Yep. And do you know what you call the ones? Yep. Woofers. There you go. Tweeters and woofers, right? And then the ones that are really low are the subwoofers, right? Right. And we have a subwoofer under that table that I'm hiding because it's attractive. The one in the pub I can't hide. You've seen it, right? The one in the pub, hard to miss. Yeah, it's a giant box. Looks like it should be a refrigerator or something. Yeah, it's pretty obvious. Yeah. All right. So here you can actually see, it's going to visualize the process that we just discussed. The what?
I'm Jake O'Neill,
this guy. Yeah.
creator of Anagraphs, and this is how speakers make sound. The basic speaker design has a motor that drives the speaker back and forth, attached to a cone to translate this movement into pressure waves that travel through the air. Let's look at each part in depth. The motor. A voice coil and magnet work together to form the speaker motor. The voice coil has a long section of thin copper wire wound many times around a heat-resistant cylinder called the former. When electricity flows through the copper windings, it naturally generates a surrounding magnetic field. This phenomenon is what makes an electromagnet. An electromagnet can act just like a permanent magnet, and yet, incredibly, its polarity, or positive and negative pole orientation, and magnetic intensity can be changed by altering the supplied electric current. It can instantly be made stronger or weaker, reversed, or turned off completely. A large permanent magnet or natural magnet surrounds the voice coil. This magnet has a top plate and a backing plate with a pole piece through the center to focus the magnet's field through the gap. An intricate electrical signal flows through the voice coil windings, causing it to move back and forth as its magnetic field pushes and pulls against that of the permanent magnet. This electrical current is a precise replica of the audio that was originally recorded. In fact, the entire sound is contained in this impossibly detailed signal. The cone and suspension. The cone translates voice coil movement into waves that travel through the air. It has its own flexible suspension system made up of the surround on the outside and the corrugated spider at its center. The dust cap keeps debris and unwanted material out of sensitive internal areas. Underneath the dust cap, the voice coil's copper leads attach to more flexible wires called tinsel leads that can smoothly deform with intense speaker movement. Recreating the whole symphony. If a speaker only moves back and forth, how does it reproduce an entire symphony of sounds at the same time? Let's look at basic sound wave operation. Air is an elastic medium, meaning that it returns to its original shape once an acting force is removed. Speakers push and pull air molecules, making them ram into each other in a domino effect. This wave reaches and moves your eardrum, which sends a signal that your brain interprets as sound. You could even say that hearing is just movement detection. While it's often easier on paper to draw waves as a bouncy line, in reality, sound waves are three-dimensional areas of high and low pressure.
When we turn up the volume, the speaker pushes harder, sending more forceful waves through the air. The sound wave's pushing force is its amplitude. To make high and low sounds, the speaker vibrates faster or slower. The wave rate is its frequency measured in hertz, or in musical terms, its note pitch. From waves to music. A musical instrument produces a unique waveform when played. Just one note has low, mid, and high range vibrations combined into a complex sound wave. The most apparent frequency of a vibrating guitar string may be a G note. And yet many smaller twitches and movements travel through the string at the same time, producing tones that your ear also detects. Here's the exact same guitar string pluck sound, but I've isolated distinct frequencies from low to high. A single instrument note is really a sandwich of frequencies where one main frequency stands out. This frequency sandwich is known as an instrument's timbre, or unique sound. It's making a G note, yes, but it still definitely sounds like a guitar and not a piano. When two or more instruments are played together, the unique sound waves combine into one even more complex unified wave. Matching frequencies from each instrument merge, becoming louder but indecipherable from the other. However, many unique frequencies from each instrument's distinct timbre remain intact and undisturbed. With a little effort, our ears can still pick out these individual instruments from the mix. The human ear can discern sound vibrations between about 20 hertz and 20,000 hertz. That's a lot of available frequency to work with. High frequencies ride on the back of rumbling bass waves to reproduce an entire orchestra in one impossibly complex, unified waveform. It's entirely possible for one speaker to handle the whole sound, like earphones, for example. However, in large spaces where sound waves need to travel further, some audio setups divide specific frequency ranges between specially designed speakers. A speaker intended for low, slow frequencies has a much different design than speakers made for high and fast frequencies.
I like that one. That was good. It's very informative. Covers all the good stuff in there. Yeah, he's got good stuff. There's a couple really great content providers out there that make some great stuff. So anyway, if you like music, if you really like good high fidelity, what does it mean to be high fidelity music? Does anybody know what that means? High fidelity. What's fidelity mean? What's it mean to be, what's fidelis? Yeah. You know?
No much.
Fidelity. Ever heard the word, you know?
Quality.
I know infidelity.
Okay, what's infidelity?
Cheating.
Cheating. Okay. So fidelity, instead of cheating, it would be, it's actually like truth. So high fidelity is like true to the actual sound. So you may hear hi-fi, that's just high fidelity. So what they're saying is if you have a high fidelity speaker, it's true to the real sound. Whereas like, if I have time at the end of this, I'll get down the phonograph. And not very high fidelity, let me tell you. It sounds really weird, but it's cool. It just sounds super weird. All right. So, and we have lots of hi-fi speakers in this house because that is Jason's jam. All right. Well, we do have time. Good. All right, so what I'm gonna do is we're gonna do a couple more trivia questions because we have all our trivia here, and then I will get out the phonograph and let you guys see it. And then I'll let you guys see if you can figure out how it's working to begin with, because it's a little different than how these speakers work, clearly. All right, let's see. All right, first question. Let's see, I will do about 10 of these. Let me see, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, question number 1. In 1943, the Supreme Court of the United States granted full patent rights to Nikola Tesla for the invention of the radio, superseding and nullifying any prior claim by this inventor. Ooh, who invented the radio? Who is, do you know?
Thomas Edison.
Not Edison. Good guess, though. Do you want to take a guess?
Alexander Graham Bell.
Graham Bell's good guess, but that's not the right one. One more guess.
Einstein.
Einstein, no. It was in a homework assignment a while back, but I actually think the juniors had it. I don't know if you had it. Marconi.
Yeah, I don't remember.
Yeah, you heard of Marconi? Yeah, Marconi is the guy who gets the credit, but maybe not so much. All right, what natural wonder did Tesla harness to power New York City? Ooh, PJ.
The Eiffel Tower.
The Eiffel Tower? Okay. Good. Oh, that's a good guess. All right, do you know?
Niagara.
That's the one, Niagara Falls, natural wonder. So all that water flowing. She's like, oh darn, it was a wonder. It is a wonder. It's impressive. All right, in the 1893 Chicago World Fair, Tesla's alternating current was used to power the entire exhibition. What U.S. president pushed the button to turn on the electricity? Guessing?
Eisenhower.
Not, oh no, he's way later. Not Eisenhower, but it's a good guess. 1893. Come on, homeschoolers, you're supposed to like memorize presidents and dorky things like that, aren't you? You want to guess? Grant? No, not Grant, but that's a good guess. Hey, he says Grover Cleveland, and he's right. Grover Cleveland, who, by the way, has like the best mustache. Y'all have seen Grover Cleveland, right? Like, it's legitimately awesome. Okay. Oh, you all know this one. Where was Tesla born? Yeah, Serbia. We got that one. Okay, he discovered the rotating magnetic field. Is this going to be Edison or Tesla? Who votes Edison? Who votes Tesla? It's Nikola. All right. True or false? Edison held over 10,000 patents. Okay, who votes true? Who votes false? Okay, it's false. He held 2,332 patents. 1,093 of those were held in the US. So that means he had patents elsewhere as well. Okay, Edison's nickname, who remembers it?
Mickey.
No, not Eddie. It has to do with where he was.
Tommy.
No, Tom. I didn't hear Tommy, but that's a great answer. I'm sorry. You said it with such conviction. You're like, I got No, y'all, he was the Wizard of Menlo Park, remember? The Wizard of Menlo Park. Okay, who said it? Edison or Tesla? It's the wireless transmission of truth. Okay, who votes Edison? Who votes Tesla? That's a Tesla. All right, and what was Tesla's nickname? The Tesla, no.
Elon Musk.
Where was Tesla? No, once he started working, not where was he born? Where was it? Where did he do? Not New York. Colorado. So he was the Wizard of the West. You had the Wizard of Menlo Park, and then you had the Wizard of the West. All right, so what I'm gonna do for you is I'm gonna find that other video that I told you about that really explains how current is moving through wires, because it's pretty wild. And I'm pretty sure it was, I think Jason sent it to my Facebook because he just sent it to me last night. So give me 1 second. And while that's playing, I'll get the phonograph out and let you guys have a real turn at like cranking it, seeing how it works. I think it's in here. I think. Oh, look at that. Look at that Facebook memory of that pupper.
Aw.
Itty bitty little dude. Aw.
Aw.
Maybe this will, at some point today, maybe this will come around. Come around. Maybe. Wow, this just does not want to load.
You can watch this someday.
I know, right? Oh, here it is. Not that one. He sent me something else. So I sent him that cool. Here it is. All right. Whoop. Here we go.
Oh, it's you.
I know, right? So cute. Okay, I'm gonna pop this here. And I'm gonna bring the phonograph down. I'm gonna have to take a second and dust it because I have not dusted it in a bit. So it's gonna be kind of gross. Okay, load this up. Well, I know, because it's not going yet. Go ahead, take that off. All right.
Imagine you have a giant circuit consisting of a battery, a switch, a light bulb,
Whoa.
and two wires, which are each 300,000 kilometers long. That is the distance light travels in 1 second.
Okay.
So they would reach out halfway to the moon and then come back to be connected to the light bulb, which is 1 meter away. Now the question is, after I close this switch, how long would it take for the bulb to light up? Is it half a second, 1 second, 2 seconds, 1/c seconds, or none of the above? Now you have to make some simplifying assumptions about this circuit, like the wires have to have no resistance, otherwise this wouldn't work, and the light bulb has to turn on immediately when current passes through it. But I want you to commit to an answer. This question actually relates to how electrical energy gets from a power plant to your home. You know, unlike a battery, the electricity in the grid comes in the form of alternating current, or AC, which means electrons in the power lines are just wiggling back and forth. They never actually go anywhere. So if the charges don't come from the power plant to your home, how does the electrical energy actually reach you? When I used to teach this subject, I would say that power lines are like this flexible plastic tubing, and the electrons inside are like this chain. So what a power station does is it pushes and pulls the electrons back and forth 60 times a second. Now at your house, you can plug in a device like a toaster, which essentially means allowing the electrons to run through it. So when the power station pushes and pulls the electrons, well, they encounter resistance in the toaster element, and they dissipate their energy as heat, and so you can toast your bread. Now this is a great story. I think it's easy to visualize, and I think my students understood it. The only problem is, it's wrong. In the 1860s and 70s, there was a huge breakthrough in our understanding of the universe, when Scottish physicist James Clerk Maxwell realized that light is made up of oscillating electric and magnetic fields. The fields are oscillating perpendicular to each other, and they are in phase, meaning when one is at its maximum, so is the other wave. Now he works out the equations that govern the behavior of electric and magnetic fields, and hence these waves. Those are now called Maxwell's equations. But in 1883, one of Maxwell's former students, John Henry Poynting, is thinking about conservation of energy. Now, if energy is conserved locally in every tiny bit of space, well, then you should be able to trace the path that energy flows from one place to another. So think about the energy that comes to us from the sun. I mean, during those 8 minutes when the light is traveling, the energy is stored and being transmitted in the electric and magnetic fields of the light. Light carries energy from its source out to its destination. But the kicker is this. Poynting's equation doesn't just work for light. It works anytime there are electric and magnetic fields coinciding. Anytime you have electric and magnetic fields together, there is a flow of energy, and you can calculate it using Poynting's vector. To illustrate this, let's consider a simple circuit with a battery and a light bulb. The battery by itself has an electric field, but since no charges are moving, there is no magnetic field, so the battery doesn't lose energy. When the battery is connected into the circuit, its electric field extends through the circuit at the speed of light.
This electric field pushes electrons around, so they accumulate on some of the surfaces of the conductors, making them negatively charged, and are depleted elsewhere, leaving their surfaces positively charged. These surface charges create a small electric field inside the wires, causing electrons to drift preferentially in one direction. Note that this drift velocity is extremely slow, around 1/10 of a millimeter per second. But this is current. Well, conventional current is defined to flow opposite the motion of electrons, but this is what's making it happen. By using the pointing vector, you find that the energy flux only goes one way, from the battery to the bulb. This also shows it's the fields and not the electrons that carry the energy.
I mean, how far do the electrons go in this little thing you're talking about? They barely move. They probably don't move at all.
Now, what happens if in place of a battery, we use an alternating current source? Well, then the direction of current reverses every half cycle. But this means that both the electric and magnetic fields flip at the same time. So at any instant, the pointing vector still points in the same direction, from the source to the bulb. So the exact same analysis we used for DC still works for AC. And this explains how energy is able to flow from power plants to homes in power lines. Inside the wires, electrons just oscillate back and forth. Their motion is greatly exaggerated here, but they do not carry the energy. Outside the wires, oscillating electric and magnetic fields travel from the power station to your home. You can use the pointing vector to check that the energy flux is going in one direction. You might think this is just an academic discussion, that you could see the energy as transmitted either by fields or by the current in the wire. But that is not the case. And people learned this the hard way when they started laying undersea telegraph cables. The first transatlantic cable was laid in 1858.
It only worked for about a month. It never worked properly.
There are all kinds of distortions when they try to send.
Enormous amounts of distortion. I mean, they could work it at a few words per minute.
What they found was sending signals over such a long distance under the sea, the pulses became distorted and lengthened. It was hard to differentiate dots from dashes. To account for the failure, there was a debate among scientists. William Thomson, the future Lord Kelvin, thought electrical signals moved through submarine cables like water flowing through a rubber tube. But others, like Heaviside and Fitzgerald, argued it was the fields around the wires that carried the energy and information. And ultimately, this view proved correct. To insulate and protect the submarine cable, the central copper conductor had been coated in an insulator and then encased in an iron sheath. The iron was only meant to strengthen the cable, but as a good conductor, it interfered with the propagation of electromagnetic fields because it increased the capacitance of the line. This is why today most power lines are suspended high up. Even the damp earth acts as a conductor. So you want a large insulating gap of air to separate the wires from the ground. So what is the answer to our giant circuit light bulb question? Well, after I close the switch, the light bulb will turn on almost instantaneously in roughly 1/c seconds. So the correct answer is D. And I think a lot of people imagine that the electric field needs to travel from the battery all the way down the wire, which is a light second long. So it should take a second for the bulb to light up. But what we've learned in this video is it's not really what's happening in the wires that matters. It's what happens around the wires. And the electric and magnetic fields can propagate out through space to this light bulb, which is only 1 meter away, in a few nanoseconds. And so that is the limiting factor for the light bulb turning on. Now, the bulb won't receive the entire voltage of the battery immediately. It'll be some fraction, which depends on the impedance of these lines and the impedance of the bulb. I think it's just kind of wild that this is one of those things that we use every day that almost nobody thinks about or knows the right answer to. These traveling electromagnetic waves around power lines are really what's delivering your power.
Interesting, right? So
what's the most
that? So two quick things. If you were to look on the wall in the pub between the where the bar ends and that little Schifferode cabinet that the phonograph is usually on top of sits, there is an antique map there of the original underwater telegraph system, not original, some good time into it, because there's a fair amount of lines running in there. What kind of cables are they using now for communicating? Submarine cables, undersea cables? Are they telegraph cables? What kind of cables are they? Any of you giggly people know? Do you know?
I know the name, but I don't remember it.
Don't remember it. So a lot of what they're using now is fiber optic cable, right? Because that's the same thing we use. So if you paid attention to the news, I just saw this morning. I think it just got released this morning. But there are at least 4 underwater fiber optic cables running through the Red Sea that have been damaged late last week. Certain companies are using the term cut. So Jason and I were talking about this morning because it was really interesting, because they're not sure at this point what happened. Some people are automatically blaming the Houthis, so it's rebel, like terrorist backed rebel thing. Like, was this an act of war, or that same group actually went over and like hijacked a cargo ship a couple weeks ago, and the ship was abandoned by the crew, but its anchor was dragging. So the anchor could have severed the cables. In either case, they're still blaming them. But it's like, I told you guys before that he's talked about how those telecom buildings are like targets. So are the undersea cables. So it'll be interesting to see how this works out in the next couple of weeks. So if you're interested in like where technology and politics go together, here's where it's going to happen. Like, is this a situation where this was done intentionally? Because they said a quarter of the communication that goes to the Red Sea has been impacted. That's huge when a quarter of your communication is impacted. And think about what the communication's used for: banking, medical stuff, governmental stuff, not just like your email and you're watching Netflix. Like, it's a whole lot more. So that's a big deal. All right, so before we turn the crank to the phonograph, has anybody ever used one before? No, I would love it. Okay, thinking about how the loudspeakers worked. This is a different kind of process. All right, so if you want to come over and have a look at it first, see what you're seeing. Turn it a little. We talked about some sound being high fidelity. I said that's definitely not. Right. So this is actually an old LP. I got this at an antique store, and it's a Mozart piece on here. That's what's on here. Actually, the Magic Flute, but it's written in French. So the way that these work, and the way that record players are a little more complex, but the basic concept is you have this little needle here, right? And when the needle is placed down on the vinyl, or it used to be wax even, it will fit into one of these grooves. Within the grooves are actually little, up and down, up and down, up and down. And that starts the vibrating, the longitudinal wave, right? And then it's going to travel through here, and then this is simply for amplification. That's all it is. So this one is so old, it doesn't have electricity that goes to it. The only way it works is you crank it, and you kind of got to keep cranking it. You can control the speed of it. Show you underneath. You can control it. This will loosen it. So it still has, because there's a spring in there, so it still has some energy to do it. And that will stop it. And this will control the speed from slow to fast. So it'll change how it's spinning. So we'll start it on slow. Pop it on there. And we'll get it. Build it up instead. Oh, you have that as good too. All right, so drop the needle on it gently. Slow, speed it up. See any better? Yeah. There's the lowest speed.
That's too fast too.
That's the lowest speed.
Probably when you crank it faster.
It's not gonna crank faster. It's holding the energy, cranking it up. But it will eventually slow down, and then it'll.
I just get my ear in there.
It would not be good. Yeah, let's see, he brought me some jazz here, what we got? By John Wilcott. John Wilcott.
No, this is just. That was not travel as far as I would think. It sounds way.
Do you have any good examples of high fidelity, of something that you could just play off your phone in there, or something that's got a good digital signal that plays through the speakers? And you've got like everything on the planet.
iPhone you would say.
Oh, yeah, but they're, I don't think they're on the system to make it go. You got something, right? So if you wanna hear how the big subwoofer sounds, I think he's going to demonstrate. We talked about the giant subwoofer in there.
Careful, you'll also break my.
Oh, thanks for the warning. Yeah. So if you go in the pub, he's gonna play the best of this.
Oh, yeah. That's the same song, but a different.
Oh, the same song.
I'm cut ahead.
No, don't get calling on the spot.
What's the favorite song? What's the favorite song? Mr. Blue Sky?
Oh, no.
Mr. Blue Sky. Can you make that work, Chase?
What is that?
I love it.
Sorry.
That's fine. How are they?
Oh, wow, yeah, that's not really low.
I can make Alexander go to the music.
Cool, y'all. Well, good. Hopefully that was fun. Hopefully it was a good lesson and you enjoyed it. Awesome. That's all everyone. Yeah. Yeah. Bye. Bye, y'all. Have a good one. Still trying to figure it out?
I figured it out.
All right. That's what I want to hear. Out.
Last week I didn't know that. Now I know how a motor works.
There you go.
Did y'all make motors today?
No, we're making them next week though.
We don't need to turn in our lab.
Nope, you don't need to turn in your lab. You're all good.
Wait, where did my lab go? Fine. I left mom here.
You have to put there in here. I'm sure something left in the books last week. I wonder if they remember this week.
I think it's Emma, because I see her bringing books. Yeah.
By the way,
I kept my ball in the class.
I know. Somebody did. You're
I keep forgetting.
You're my culprit. Yeah. We have all these different options. Like all these see like sunrise. Meteor shower. Oh, we didn't make. We lost. Then you can all like. This. Green. And then I have like. These are the active, the special, like,
Ah, excuse me.
Yeah, there's that. Why did that eat back? Later. And then I have like the DIY one, I thought that this one was the impossible one. And my mom was old, and then he does that, and makes it so much longer. So no, run it all, stretch it out. I made look at this real quick. Give her your rating glass. Got some here. Now it. That's all that. What are you doing?